So we're simplifying radicals today, and for some of you this is going to seem somewhat familiar because maybe you got to it back in Algebra 1 or something. For others of you, maybe not. Either way, that's fine. The basic idea is that we should be able to simplify stuff we couldn't have been able to simplify otherwise. So for example, by the time we're done with this kind of work, you're going to be able to simplify, for instance, root 500. If I gave you root 500 over 5, we can actually simplify that, but it is not going to be the square root of 100. We can't just take this, like the 500 that's inside the radical and divide it by something that's outside. So there's some techniques that go with how we simplify a radical, and it does not mean calculating a decimal. When we talk about simplifying a radical here, we're going to just leave it in radical form. We're just going to make it into a radical that we can actually work with much easier. Again, not decimals. So, for doing this first one, there are a couple different methods. We're going to start by looking at the largest perfect square method, which basically means I'm going to look at that 500 and I'm going to look to see what is the biggest perfect square that multiplies into 500. Now, of course, that means you got to know your perfect squares, right? You remember those? Most of you, yes, but if you don't, you could always start these types of problems by making a list of the perfect squares on your own. Like 1 squared is 1, although we're not going to try dividing by 1, or we'll just repeat ourselves over and over again. 2 squared, of course, is 4. 3 squared, 9. And then 4 squared, and then we just continue on the same way. And so if you do this, then you can actually get a list of perfect squares. And what we're looking for here is the biggest perfect square that multiplies into 500. And we'll often say that goes into it, but when we say goes into it, we're really meaning multiplies into it. And of course, that list of perfect squares goes on and on and on. Out of that list, though, one number should jump out right now as going nicely into 500. Which is that? 100, yeah. 100 goes into it. Now, you might also have seen that 25 goes into it, but we want to know the biggest of them. And so that's why we'd go with the 100, because we want the biggest perfect square. So what I'm going to do first then is I'm going to break my 500 into being 100 times 5. Now it's the square root of 500 though, so I keep the square root symbol over that. And then the reason why I want to do that is because I can then turn it into the square root of 100 times the square root of 5. Now, when you get doing these and you get a nice rhythm going on, you'll find that you don't really need to write this line every time. You'll typically go straight from the original problem down to that line. I just want to make sure that we see why we're able to do that by drawing that in there the first time. Now, the reason why we needed a perfect square is because I can now simplify one of these radicals. Do I know what the square root of 100 is? Yeah. The square root of 100, of course, is 10. Do I know what the square root of 5 is? No. That's some decimal. And so then that stays as the square root of 5. And so then 10 times the square root of 5, or what we tend to just say 10 root 5, that is our final answer. That's what we're looking for. So this problem is now done. A little side note, though, before we go too much further. The square root of 5, are there any other perfect squares that multiply into 5? No. Well, 1 does, but that doesn't count. And 4, it doesn't divide into 5. So that's how we can know that we did, in fact, find the biggest perfect square that went into 500. Because if it wasn't the biggest one, there'd be another perfect square that we could take out of the 5. All right, so having done that one now, you've seen the basic process. I'd now like you to try using that same process here with the root 98. So go ahead and start working that one through to find the biggest perfect square and then simplify it down. All right, and again, we want to look for the biggest perfect square that multiplies into 98. Well, definitely something bigger than 98 would not work. So that means I can rule out a lot of perfect squares right there. All right, now I'm looking for the biggest one, so I'll start at the big end. If I do 98 divided by 81, do I get a whole number? No. So 81 can be ruled out. If I do 98 divided by 64, do I get a whole number? No. so that also can be ruled out. If I do 98 divided by 49, does that give me a whole number? Yes. So then that means that 49 is my biggest perfect square that goes into the 98. So I'm going to split root 98 into root 49 times root 98 divided by 49 is 2. All right. Now again, I simplify any of the square roots where I actually know what the value is. Do I know what the square root of 49 is? I should. It's a perfect square. Yes. Square root of 49 is 7. Do I know what the square root of 2 is? No, I do not. And so that's why that one just stays root 2. Therefore, that is your final answer. That simplifies down to be 7 root 2. Now these first two, again, these were using the largest perfect square method, where we would just look at it and try to find the biggest perfect square that goes into it. Which is great if you can just look at it and know what that number is. But sometimes we can't. In fact, sometimes they're much more involved. We're going to take a look at one other method for being able to do it, called the factor tree method, also known as prime factorization. And so we're going to simplify this radical by breaking it up into its smallest pieces, basically, is the way this is going to work. Now, I call it the factor tree because I actually will draw out a factor tree for this and give myself room to write. So I need two numbers that multiply to give me 432. It can be any two numbers. It doesn't matter which two you start with, just not 1 times 432, I suppose. All right, so we break out the calculator, and there's lots of different possibilities you might come up with. The one that I just heard was 16 times 27, so we'll go with that. All right. Then I break each of those numbers up, and I'm going to keep breaking them up until they don't break up anymore. So for instance, 16. Which two numbers do you want to use for multiplying to 16? You got a couple options. We could do 4 and 4, or we could do 8 and 2. Yeah, go with whatever you like. I heard 4 and 4 of those, so I'll go with that. Does 4 break down more? Yes, it does. 4 breaks down into 2 times 2. And, of course, the other 4 will also then break down into be 2 times 2. 27, does that break down more? Yes, it does. 27 would be 3 times 9. Now, does 3 break down anymore? No, it would just be 3 and 1. And we don't need to worry about going to the 1s. Or again, we'll just go into infinity of 1 times 1s. But the 9 does. That becomes 3 times 3. And so then, this would be our factor tree. You'll notice at the end of every single one of these branches to our tree, we have a prime number. We have 2s and 3s in this particular example. And what we're going to do now is we're going to list out all of those prime factors in order. And yes, we always want to put them in order because it makes it easier to keep them all together. So I'm going to list out all my 2s first. So I'm going to do 2 times 2 times 2 times 2. I had 4 2s, so I need to list out all 4 of them. How many 3s do I have? 3. Yep, so I'm going to do times 3 times 3 times 3. This number right here, 2 times 2 times 2 times 2 times 3 times 3 times 3 equals 432. So all I've done is rewritten my original square root in its component parts. The reason why we want to do that is because I now can actually figure out some square roots very easily from this. Because, for instance, this 2 times 2 at the start. Well, what's the square root of 2 times 2? Well, 2 times 2 is 4, and the square root of 4 is 2. So the square root of 2 times 2 is 2. So I can actually take that outside of the square root. So basically then what I'm looking for then is any pairs that are inside the square root. Those can come outside of the square root because I can actually take the square root of them. And so the same thing would happen with the 3's as well, where the square root of 3 times 3 would be 3. Now notice what was not circled here. There was a single 3 that was not circled. Therefore, since it was not circled, it has not been pulled out of the square root. Therefore, it is still inside of the square root. And so then, this is our breakdown. We do have one last step, though, with it, and that is to actually do the multiplication. On the outside, I can do 2 times 2 times 3, which is 12. And inside, if there were multiplication, I would do it, but since it's just a 3, I just leave it as the 3. And then that is done. That's my final answer that I'm looking for here. I'm looking to just get an answer of 12 root 3. All right, so having seen how that one was done, I would like you to also try using this method on our second problem, the square root of 840 over here. Even if you like the first method that we did first, please try the factor tree method with this just so that you give it a chance, because there are pros and cons to each. All right, now you might still be working on your factorization here. If so, we'll probably finish about the same time, but I'm going to go ahead and start doing my prime factorization. So when I look at 840, since it ends in a 0, the first thing that jumps out to me is 84 times 10. So that's going to be my first factorization. But if you even use a different pair of numbers to start with, you will still end up at the end in the same place. All right, so I'm now going to break those down. 84, I could turn that into 4 times 21. So then the 4 breaks up into 2 and 2. 21 breaks up into 3 and 7. And notice, all of those are primes. None of those break down any further. So I know I'm done with that side. Then I go over to the 10. 10, of course, is 2 and 5. Both of those are also primes, so those are also done. And so now I just need to go and grab all of those prime numbers, and I'm going to write them all out in a row here. So I need to start by looking for how many 2's I have. And you notice that I have 1, 2, 3 2's. So I'm going to write all those out together. So we're going to do 2 times 2 times 2. Then I look for any 3's, and I have a single 3. So that's going to be times 3. Then we got a 5, but only one of them. And then finally we have a 7. So I do times a 7. Now remember, that is breaking up the 840, so all that stuff is still inside of the square root. Now I can go ahead and look for the pairs. And in this case, notice there's only one pair, just that pair of 2's. But anytime I have a pair, I can pull that outside of the square root. And then left inside is anything that was not circled. So that's going to be the 2 times the 3 times the 5 and times the 7. Now, last step is we clean it up. We do the multiplication. And on the outside, there's no multiplication to do in this case, so that's just going to stay a 2. On the inside, though, we can multiply the 2 times 3 times 5 times 7. That gives us 210. And then that is our final answer. Now, which method do you prefer? Well, it's a personal preference thing, but sometimes you'll also find that it depends on the numbers involved. In this particular case, if you had started by just looking at the list of perfect squares, and you had been dividing 840 by every single perfect square underneath it, you would have been checking a lot of numbers. Because you would have been looking up through that list of numbers and getting smaller and smaller and smaller until you hit the very smallest perfect square that we would actually consider, which was 4. Now, you could have done it that way, but it probably would actually have taken you even longer in this case, because you would have to check so many different numbers. So in cases like this, the factor tree works really well. But again, personal preference for which one you want to use going forward. So now you can go ahead and choose your method as we start simplifying a couple more here. And we're going to start with these. And the first thing you might notice here is that that first problem has that 3 out front. And so you're probably wondering, what do we do with the 3? But the nice part is that really, for the moment at least, we can ignore the 3. And you can just focus on simplifying what is the square root of 128 using either of the two methods we've looked at. So go ahead and just start. Simplify the square root of 128, please. Now, if you had chosen to do this one by making the factor tree, you would have gotten a whole lot of 2's. 7 of them, to be exact. And so then you would have started circling pairs, and so you'd notice that you got 3 pairs of 2's. So I'd have 3 2's on the outside of my square root. And inside was anything that wasn't circled, which was a 2. And so we'd have 8 times the square root of 2. You also could have gotten there with the biggest perfect square method. You would have said, okay, what's the biggest perfect square that goes into 128? And that would have been 64. So you would have had root 64 times root 2. And then you would have then gotten to the 8 root 2. Either method is fine. But remember that I was ignoring that 3 that was out front. And we got to come back and see what that 3 did. Well, that 3 that was hanging out front here, it really just kept hanging out here. And so even down here, I still have that 3 times those numbers. Well, you can see then what our last step is going to be. I need to now do 3 times the 8, which gives me 24. And that does not affect the square root of 2 because the 3 is on the outside. And so then that is our final answer. It's just 24 root 2. All it means with having the number out front is that we just do a little bit of multiplication with that. And you even, yes, could have done it from that point. Now, with that one being done, seeing how that one is done, take a moment, look to simplify this 10 root 41, please. So as you're looking at it, like let's say you're doing the biggest perfect square method. The biggest perfect square that is less than 41 is 36. So that's where I'd start by doing my dividing. If I do 41 divided by 36, do I get a whole number? No. By 25? No. 16? No. By 9? No. By 4? No. There are no perfect squares that go into 41 other than 1. And in fact, in general, there are no other numbers that go into 41 than 41 and 1 because it's prime. And so what do we do in that kind of a case? What do I actually say is my answer? Should it not be simplified at all? My answer would actually just be the same thing. It'd be 10 root 41. I wouldn't want to leave it blank because blank says I don't know how to do it, or I'm skipping it, or something like that. This actually means that is the simplified form. Having done those, we now can actually launch into something that is going to be new for basically everybody. Whereas even if the other stuff was kind of old and familiar, this should not be, because we're now taking a look at the square root of negative numbers. And before today, our answer was something like this would have just been to say we can't do it. The square root of a negative does not exist. And that's true. There are no real solutions for the square root of negative 36. It's not a real number. But you'll notice I'm having to specify that it's not a real number. It is possible for us to come up with numbers that are not real. And actually the way that we get numbers that are not real is by trying to take the square root of a negative. So what do we call these non-real numbers? Well, they exist, but really they only exist in our minds. They can't really exist as an actual quantification of something in reality. And so we call them imaginary numbers. This should go into your notes here. And as you take a look at these notes that you've written down, the single most important thing for you to know out of this set of notes is this simple little definition of I. I equals the square root of negative 1. You may or may not have noticed previously that your math teachers, when choosing variables, generally did not choose lowercase I as a variable. This is the reason why. I is actually reserved to always mean the square root of negative 1. And so we don't want to choose it as a variable for that reason, because we'd actually be using it to represent this number, not the variable. Now, because I equals the square root of negative 1, it then allows us to quantify some other values. Like the square root of negative 4 then would equal 2i. And we'll look here in a moment and see how we actually get those numbers and how that process works in order to be able to get there. But you need to remember that I equals the square root of negative 1 here. And it's always negative 1 for I, hence why this is a 2i and not just an I there. All right, and then a little bit of other vocabulary there. Those are imaginary numbers. Complex numbers can also occur where we mix by adding or subtracting imaginary and real numbers. So that's what makes something complex. All right, so let's go back to those two that we saw in the first place. We're going to now look at how we would actually go about the work of simplifying the square root of negative 36. So, in order to simplify this, the very first thing that I want you to do, because there's that negative inside of the square root, is to rewrite it as 2 square roots, just like we did with the other ones, except make one of those square roots the square root of -1. Because by pulling that out, it's going to allow us to deal with the rest of it, which in this case is the square root of 36. Now this particular one, it actually is a little bit more straightforward, because in order to simplify the square root of 36, all we got to do is take the square root of 36 because it's a whole number. So the square root of 36, of course, equals 6, and the square root of -1. Do we know what the square root of -1 equals? Yes, we do, because we just wrote it down to our notes. That is I. And so it is going to be 6I. And that's our final answer. And so we would approach the next problem in the same way. And so the very first thing we do is we are going to split it up into 2 square roots here. Remember, one of those square roots, because there's a negative inside, has to be the square root of -1, leaving the other one to be the square root of 150. Now in this case, we cannot just say what's the square root of 150. It's not a whole number. So instead, this is where we're going to be simplifying that radical using the methods we looked at earlier in class. Either the perfect square method or the factor tree method. Pick your favorite and go ahead and simplify the square root of 150, please. Now, if you did this using the factor tree method, then your 150 would become 2 times 3 times 5 times 5. And then you just have one pair here that comes out. And so then that would be 5 times the square root of 2 times 3 times the square root of -1. But if you had done it by the biggest perfect square method, then you would have said, well, the biggest perfect square that goes into 150 is 25. And so then you would have written it as root 25 times root 6, which you'll notice would give us the same thing here of 5 root 6 for our square root of 150. Now the square root of -1, you'll notice that that's just been carrying down as it is. But since I simplified everything else, I might as well simplify that now. What does the square root of -1 equal? I. Yep. But I generally don't like to leave the I written last, because you notice that here, the way I wrote it, it looks kind of ambiguous about whether that I is supposed to be inside the radical or not. By the way, it always should be outside. But it looks kind of ambiguous right now with it being there. And so rather than just trying to space it out a long ways, to give our final answer, we actually always want to write the radical part last. So that means that I'm going to reorder this so that the 5 and the I come first, and then the radical, the square root of 6, comes last there. So this would actually be our formatting then for our final answer.